Welcome to video 3. The objective of this video is to do a deep dive into artificial intelligence. As we've seen in the previous video, this is one of the major general purpose technology that will have an impact on the world around us, and particularly on healthcare. So it's essential to get a better understanding of the opportunities and challenges associated with artificial intelligence. I'd like to start with a paradox that was coined by somebody called Moravec and his team, Brooks and Minsky at the MIT, a number of years ago. And this paradox is quite counterintuitive, and I think it's a good way to start to actually apprehend the concept of artificial intelligence. The paradox was stated as such: contrary to traditional assumptions, high-level reasoning requires very little computation, but low-level sensory motor skill require enormous computational resources. What does that mean in simple terms? It means that it is comparatively easy for a computer to exhibit adult-level intelligence, but it is very hard or nearly impossible in some instances to give them the skills of a 1-year-old when it comes to perception and mobility. Meaning that a little 1 or 2-year-old kid probably has a better level of mobility than a robot, and is able to grasp an environment and learn faster and better than those robots. So we're not there yet, especially on the robotic side. But we're making a lot of progress, and some of you can check the Boston Dynamics video. It's very impressive progress in the field of robotics. Now, that said, on the human level intelligence, we have machines which are able in narrow fields today to actually beat human in complex tasks like playing chess, like Go game, and many other tasks around, for example, analytics and big data, which is not currently possible by a limited biological brain. Now, I would like you to understand artificial intelligence and the different concepts mapped on a continuum. If we look at the continuum based on the concept of autonomy, you will see on the slide on the top that human on the left side, fully independent human, decision-making and ability, and on the right side, you'll see full machine, when the machine is totally autonomous. And in the middle, you have what I call the human-machine collaboration, or what MIT calls the collective intelligence. This is once humans have actually, perform a task, this is when AI is going to come and actually validate this task or assist human in performing the task by providing information or vetting that information. Then you move from human-machine assisted to what we call machine-human assisted. So there in that spectrum, AI is actually performing most of the task, but human is actually providing oversight and ensuring that actually AI is going in the right direction. So if you look at this spectrum, you'll move from human to human-machine assisted or AI assisted. Then you will evolve to what we call AI human oversight or human assisted. And then you'll migrate to the final stage of maturity of AI into full AI or full machine autonomy. So you can think about on the full right side for full autonomy, an autonomous vehicle which is just driving around in full autonomy, right? Now, if we map AI on a continuum, but not this time of autonomy, the spectrum is a spectrum of intelligence. We'll start on the far left with what we call automation, simple task. I just take a task, an activity A, and I just move, let's say, an object from point A to point B, and I'm going to automate this task. It doesn't require intelligence. That's the basic called automation. Also known as robotic process automation, RPA, very much utilized in process enhancements and simplifications. From there, you'll move to what we call ANI, which is artificial narrow intelligence. That's a form of artificial intelligence which is extremely strong at doing one specific type of activity. We talked about chess. That's one example. This AI is just great at doing chess, but don't ask it to book a hairdresser appointment for you, right? It does do chess. That's what it does. But the level of intelligence in that field is extraordinary, and that's a narrow field of intelligence. Now, when we're able to then suddenly start connecting different forms of algorithms together and generating an advanced form of intelligence which has a broad skill set, very much like human, we're going to move in what we call AGI, artificial general intelligence. Think about a machine intelligence which is quite similar or equal to what the human can do today. And then we'll move to the last level, and at the level of AGI, artificial general intelligence, full autonomy is expected. When you move to the last level, which is called artificial superintelligence, this is the point at which machines are generating what we call recursive self-improvements. They are improving so fast on a constant basis that they drastically outperform human beings. We're not going to talk about this during our presentation. A number of people know this as being called a technological singularity, point after which, to be honest, I don't think anybody can predict what's going to happen. A lot of people are scared about this time. I think we should look at AI as a friend And most of the work we'll be performing during our lifetime over the next 10, 20, 30 years is going to be in the top box in what we call this human-machine collaboration. In a few areas, machine will be autonomous. They may be autonomous faster than we believe, and that's something important for you to understand. Remember Asmara paradox? We have to stop thinking linearly and think exponentially. Really important to understand that, and most of the work you'll be performing will be probably in conjunction with machines. And you have to get ready to understand better of those machine work, and so that we can really leverage machine-human collaboration. Recent research at MIT has demonstrated that human in isolation or machine in isolation are not as strong as human and machine working in collaboration together. This is when we can harvest the most potential of AI. Get ready for it. This is why we're going to do a little deep dive in a subset of artificial intelligence called machine learning. So machine learning has three different dimensions: unsupervised learning, supervised learning, and reinforcement learning. I'll start with unsupervised learning. Unsupervised learning is pretty much not, you don't know what you don't know. And you're going to ask an algorithm to plow through large amount of data and find underpinning trends, structures, features, and from there organize them in the way that makes sense to us. Our brain is not able, in a trillion sensor economy, remember IoT, our IoT video, is not able to actually plow through such a large amount of data and identify trends. So there's a lot of underpinning trends. Machines are very good at that, and that's what unsupervised learning is. Those algorithms are going to plow through those large amount of data and are going to elicit features and help us understand the trends. One common utilization is what you can see on the left side, what we call recommender system. So let's say white, Caucasian, 45-year-old male, loving technology, living in Europe, that'll be me, would love Black Mirror, which is a series in Netflix talking about the, some of the negative impact of technology and protecting yourself in the future. And when I go on Netflix, actually, they'll tell me I'm 98% likely to like that series. Why? Because they understand some of the underpinning features in a large number of data, and from an unstructured data set I've created, identified trends, and now know what I'm more likely to like. And that's really interesting. If we move to supervised learning on the right side, what you'll find here is a very different environment. The machine, unlike the first set, are not just unleashed on a large amount of data. What we need to do is we need to train the machine. So they're going to be in what we call a training environment, also nicknamed fitness environment. Think about like a fitness club for the machines. They don't know like a 0-year-old kid, so we need to educate those machines. What we're going to do, we have human. It's a very human-intensive task, supervised learning. That's why the supervised is the human component. I'm going to take the example of image recognition. So let's say we want the machine to understand and see among thousands of billions of images, what is a cat versus what is a dog. But the problem is the machine has no clue what a cat or a dog is. So we need to educate the machine and train the machine. So what we're going to do in this fitness environment, we're going to actually submit images to the algorithm, and we're going to label those images. This is a cat, this is a dog, this is a cat, this is a dog. And after reviewing hundreds, thousands of images, the machine is actually going to form an image or a concept of what a cat looks like and what a dog looks like. And when it's ready, we can then utilize the algorithm on real-world data, and it's going to be able to tell us, hey, here's a cat, here's a dog. And also, the machine will keep improving as it works. We can use that in the daily life. For example, image classifications. We use it every day. Or I'm thinking about forecasting. Think about meteorological forecasting or financial forecasting. Very useful tools. So very good for predicting and anticipating. And then we have at the bottom what we call reinforcement learning. It's another way of working. This one is more think about an incentive mechanism where you're going to reward a machine by, let's say, giving them a carrot or a point. Or you're going to punish the machine by taking a point away or using the stick and saying that's not where we would like to go. So reinforcement learning is an incentivized system, incentivization system for machine. And you can guide machine in one direction or the other. So it's very effective, for example, to train robot to navigate. If the robot keeps going left, we're going to give them a non-incentive to go left, but an incentive to go right and navigate differently. Or think about game AI. If you're a gamer and using video games, you're often playing against the video game itself. It's a machine. But they use those type of reinforcement learning like decision trees and path-finding solutions in order to optimize and beat you at the game. So those are great ways of approaching machine learning. Now you need to understand with those opportunities, there are ethical and challenges attached to it. So if you look at unsupervised learning, one of the way I could actually cheat or fraud the data and the outcome of what is going to be is actually offer a data set to the algorithm which is biased in nature. Let's say I'm going to offer a data set which only contain male information, right? The machine is going to learn from that data set and think that the world around it is actually comprising mostly of male. And he's actually going to discard systematically female subject in his decision-making process because there was a bias induced in how the data were structured in the first place. So either this bias can be unknown, so we didn't realize there was so much data, we just submitted to the algorithm and it was not willful, or it was known. You can imagine a developer actually knowing that I'm going to actually submit this data set which is naturally biased. So the machine is going to go in one direction learning from a very specific type of data. And that's a way that you can actually defraud the data in unsupervised learning. If you look at supervised learning, for example, one of the ways to work with the person which is labeling or tagging in the fitness environment, remember, it would be a bit like the carer or the parent training a little kid. If I train the kid in the wrong way by tagging things improperly, the kid will actually learn from that improper manner. So it's the same as a labeler. Instead of labeling the cat a cat, maybe I label the cat a dog. And the machine is going to think that the cat is a dog. I've been actually cheating or frauding the system by improperly labeling the data. And the last one at the bottom, one of many examples, how fraud or ethical challenges and dilemma can be actually realized in reinforcement learning. Remember the incentives about the robot going in one direction? I could actually cheat on the incentive, and actually the robot should go in one direction. I could actually incentivize it to go the other way, or an algorithm to actually make a decision, incentivize the algorithm to choose one outcome versus another because I've incentivized the algorithm to go in this direction. For example, choose one given drug versus another, or it diagnose one disease versus another, or applications, ethical challenges that could be seen in the field of digital health in healthcare around reinforcement learning. Now, let's do a little dive into a subset of machine learning, which is called deep learning. Deep learning sounds complex. It's not very complex, in fact. It's just a subset of machine learning. And I'd like you to look under neural networks on the top left part. You will see here the feed forward. It's very simple. So all the different neural networks that you see, it's a simple classification of neural network, which are particularly like. In yellow is the input layer. Always look at it vertically. So an input layer, that's where the data are coming in yellow. And then in red, this is the output layer. This is where the outcome of the result of the algorithm is coming out. And you can see in the middle, in the concept of the fast forward, you can see actually a green layer, one layer. So an input layer, a processing layer in green, blue, or pink, and then an outcome layer. This is a simple level of neural network. By the way, those neural networks are based on how our brain operates with different neurons, which are connected together and create a network of neurons. We've been doing a mathematical representation of those neural networks inspired from the brain and how the brain works, and created a mathematical model called neural networks or deep learning. Why is it deep? It's because you can enhance the capability of processing by adding more layers. And you can see if you go below and then on the right side, the network are actually expanding to have more and more intermediary layer. The more intermediary layer you are, the deeper the network, hence deep learning. And the more processing capability. The only thing you need to know, and you'll see most of those networks in maximum of 7, 8 layers. A study has demonstrated that above 8, 9 layers, a maximum 10 layers, then you have an incremental decrease in productivity and the outcome. So we're usually trying to stick between 0 and 8, 9 layers maximum. So that's what deep neural network is about. I'll just pick 3 simple examples for you to understand and grab those networks. Very simple concepts. So we'll start with CNNs in the middle top, convolutional neural networks. Convolutional neural networks are a simple form of neural networks which are inspired from animal, in particular birds, but also other animals, visual cortex. And as you know, the brain is just not one entity. It has a large number of subsystems which are connected together and specialized in different areas. The speech, the vision, the hearing, etc., the thinking. So the visual cortex is specialized in identifying pattern, classifying data, etc. So now you can understand why convolutional neural network are classical network, which are used in the field of image classification. Another area in blue on the left, you'll see the recurrent neural network RNNs, and one of the cousins, the close cousins on the right side with the long short-term memory LSTM. Same classification, same families. RNNs are inspired from the auditory cortex, so how we hear things. And they're very effective in order to actually identify sounds, speech, machine translation. That's probably what you use every day when you use, let's say, Google Translate, or when you use Alexa, Siri, and other type of NLP, natural language processing interfaces, because those networks have actually specialized in understanding pattern, speech, and recognition. And then I'll take a last one, just below the pink one in the middle, somewhere in the middle of the graph, you'll see the GANs, G-A-N, for Generative Adversarial Network. And what is interesting with this one is, unlike the others, you'll see a red layer in the middle. So you'll see the yellow, the green, the red, the green, and the red again. Why is that? It's because you have two networks attached to each other, right? And that's what makes it very interesting, especially in the field of creativity. And it's something that we thought machine could not do. Actually, with the generative adversarial networks, machine have the ability to then create. How does that work in simple terms? You have the first network, which is the generative network. That generative network is going to come with ideas. So let's say we'd like to design a face, right? From scratch. That generative network is going to create face out of nothing. And is going to submit it to the second part. That's why you have a red output. And it's going to become the input of the second layer. And that second layer is the second part of the network. Is going to look at this and say, okay, hold on, here's my data points of faces, human faces. Is this one looking like a human face? No, it doesn't. And it's going to keep rejecting until the generative network is managing to fool the other network. And the day it's been fooling the network by actually creating many, many different instances of a face, for example, the network is going to say, hold on, it really looks like what I have in my data set. Yes, I approve it. And that allows us to create from scratch, let's say, pictures, images, which never existed before, face of people that do not exist. And you've heard a lot about that recently with some of the deep fake, which are video or image, which are being animated, or either new faces being created to actually pretend they are people existing when they're not. They're actually fake people. Deep fake are leveraging generative adversarial network technology. So before we conclude this video on artificial intelligence, I'd just like to tell you that, remember Asmara paradox? What you thought was not possible is actually possible. And areas of creativity that we thought were only possible for human beings are now starting to be achievable by some machine. Think about music, think about painting, think about all those areas. So the first, on this slide, you'll see the Schubert Unfinished Symphony. Unfinished because the latter part of the symphony has never been completed. Huawei, which is a Chinese manufacturer of mobile phone, but also a very advanced AI technology, managed with one of its later generation Huawei mobile phone AI chip to actually finish the Unfinished Symphony. And it was actually presented in a symphonical orchestra, I believe, in Berlin and in London. The next generation Rembrandt, that's a project by Microsoft, which has actually been thinking, hold on, Rembrandt produced 200, 300, 400 paintings during his lifetime. What if it was alive? He was alive. And then they use an advanced GAN, a generative adversarial network, to leverage the 300 or 400 paintings from Rembrandt and recreate what the next Rembrandt would look like. It's probably an average, but it's quite impressive. And if you go and look at it in the Netherlands, it's now currently displayed in a museum, you can even touch it and feel the volume because they went further than AI. They also 3D printed it the same way that Rembrandt would have printed it, by using a machine vision algorithm to identify where Rembrandt would put more volume or more light. And actually they 3D printed the next Rembrandt. So not only it's visually interesting, it's also a feeling that you can touch. Very interesting experience. Fragrance for millennials. This one is a project between IBM and Simrise. One of the things that we think human can do, and only us, is what we call the nose. Nose are those experts which have this very specific nose. They work for agrochemical company, they work for example, perfume company, and they are the only one to really sense, more than others, what's around us. What they've done with this is a company came and asked IBM to actually create from scratch for a given population, millennials, the millennials population so the young people in Brazil, with the target to launch in 2019, so that's coming as we speak, launched the first AI generating perfume. And what they did is they loaded millions of scents from vegetable, from food, from perfume inside, and then they combined it with the expectation of millennia in order to produce the first AI generating perfume. Quite an intense experience. Maybe we don't like it, maybe it's the worst perfume ever, maybe it is the best. We now have to realize that AI can do things that we've never been able to do before. Sculpture, another area. So this one is a Gaudi-inspired sculpture called Thinking Structure, entirely generated by an AI algorithm. And you can see color. The color is evolving using an algorithm that we call sentiment analysis. So people surrounding the sculpture or on social media will have different feelings. And this sentiment analysis will perceive the feeling and it changed the color of the sculpture, entirely AI generated by IBM Watson. Think about movies. Movies is a very interesting area as well. We think we're the only one to be able to script a movie and do it. This one is Sunspring, and this young actor you can see is not really an actor. It's a gig working in a tech company that wanted to play as an actor in this first AI scripted movie. We fed a GAN network with about 300 scripts from different movies, and it came out with a script from a new movie. I'm going to be honest. I watched the movie. It doesn't make any sense, right? And it took me some time to really understand what the meaning, but it is the first step toward a form of intelligence that is able to actually work also on movie. And then last but not least is AI-generated video games. Video games, very complex environment, and NVIDIA, which is one of the world leader in AI chips for video games, has actually produced entirely with AI a video game which is surprisingly realistic to a point where reality is merging with virtual reality. Fascinating experience. And maybe the last thing that you think is not possible and that could become possible is what about your next boss is a robot? What about your next employee or your next colleague is a robot? What about your next board member is an algorithm? Those things are actually real. So the example of the algorithm, a couple years ago in Hong Kong, an investment company realized that the 12 board members they had were not making optimal investment. And in order to manage this sub-level of optimum investment, they wanted to have a bit more rational decision making. So they appointed an algorithm to be a formal board member of this investment company. It has so far made quite a few investments and decisions, and it has a voting right equal to the other board member. Quite a fascinating evolution. And then what about your next colleague or your next boss or your next employee? It is already the case that in a number of organizations we're moving towards what we call digital workforce, where a number of autonomous entities, from the very simplest one, like a robotic process automation, is performing a large number of routine tasks for us, to the more evolved, where you have very advanced personal assistants and artificial intelligence algorithms which are exchanging with us, exchanging with our customers. In the banking industry, for example, as well in a few other industries, we already have a large number of interactions as high as 2 million for a few of them per year are performed solely through algorithm with the customer base. So we have to be ready from this merge of the physical digital world and from the evolution towards a world where, remember, human-machine collaboration is going to be central. If you're interested in learning more about those technologies and their application, please check out my other videos on the topic. Thank you very much.